In this lecture, we're going to learn about procedural knowledge, including how to define it, and we're going to discuss the ACT theory, adaptive control of thought, which is a three-phase model on how procedural knowledge is acquired. But let's begin first with the definition. What exactly is procedural knowledge? Well, it is our knowledge of actions and how to do things. How is procedural knowledge represented? It's represented as if-then statements. If condition X applies, then you perform action Y. If a bug is on your arm, then you slap it. Now we'll discuss the acquisition of procedural knowledge using the ACT model. It was a model developed by Anderson, which states that procedural knowledge is acquired in three phases. And these three phases include the cognitive phase, the associative phase, and the autonomous phase. Let's begin with the first phase, which is known as the cognitive phase. And it has several characteristics. The first characteristic is that procedural knowledge in the cognitive phase is initially stored as declarative knowledge. That is, each step is learned separately as a chunk of declarative knowledge. It's acquired through accretion, meaning you're just adding it to your current knowledge. To perform it, it should be translated into action. And I mean translated literally. You should read a set of directions on how to perform. Now, why would you not want to leave learning at this phase? Well, because it places a heavy demand on working memory. And it leads to slow, stilted performance because you have to stop and remember each step in the sequence. For example, when remembering a recipe, such as pancakes, as in this example, you have to remember each ingredient and step separately. And each of these is a piece of declarative knowledge that you string together into a sequence. Which leads to the next phase, known as the associative phase. This is when procedures form after repeated experiences using the declarative knowledge. Eventually, the procedures no longer require use of the declarative knowledge. They start to string together. Through repeated use, two things happen. Errors in initial understanding are detected and corrected. And second, the connections between the steps in the procedure become stronger. As a result, a true procedure develops. Why are true procedures preferable to declarative representation? Productions do not have to be interpreted and therefore are less demanding of working memory. And finally, as a result, performance becomes more rapid and smoother. The third and final phase is known as the autonomous phase. With continued practice, the procedure becomes automatic, and formally separated productions in a chain are combined into a single unit. So if you think about working memory capacity and cognitive load, you can only fit so much information there. In fact, the exact number is between 5 and 9 chunks of information. When first learning a procedure, each step is a chunk of information. However, as you learn it and it becomes automatic, each step that was originally a chunk of information is combined, and the whole sequence can become one chunk of information if it becomes automatic. And following that, two other things can occur. First is generalization. The production applies more broadly. You can use this sequence in a different context. And next is discrimination. Rules become more specific, so you will apply only when appropriate. However, this requires feedback. Take a moment in your notes and think about any example or experiences that you've had teaching or learning about procedural knowledge. And next, think about why is ACT important or useful. When you're finished taking notes, we'll move on to the next slide. Just go ahead and press play. Now we'll discuss some ideas for why ACT may be useful. Students must develop an accurate and elaborative declarative representation of the actions and conditions. To do this, a teacher must tap existing knowledge so that the initial representation is meaningful and elaborated upon. Be sure to point out both the steps in the procedure and the cues signaling when it should be used. A second implication is to provide practice. Practice, practice, practice. And of course, feedback with each of the opportunities to practice. This does at least two things. First, the feedback will help correct errors in the procedure and or conditions and help confirm the parts that are already correct. And second, it fosters the development of productions. A common shortcoming of instruction is failure to provide sufficient practice to develop true productions. And finally, continued practice will be needed if we want the procedure to be automatized. Here's an example of how to teach a procedure. Specifically, how would you teach students to compute the average? First, help students construct a declarative representation of the conditions and actions. For instance, if you are faced with a statistic problem, then identify the type of problem. Is it an average, mode, median? If it is an average, then add the numbers. If you have the sum, then divide the sum by n, or the sample size, and write the quotient as your answer. Finally, continue practice with feedback to develop automaticity. And now we'll end with some specific implications for teaching. Teach each step separately first as pieces of declarative knowledge. They have to have each step memorized if it's to become automatic and they are to become good at the procedure. Next is practice, practice, practice. We often don't give students enough time to practice procedures so they can truly become good and automatic at it. Feedback. Feedback is so essential. You should give feedback at each opportunity of practice. And finally, gradually reduce assistance. This way they'll have to rely on their own skills and abilities until it becomes automatic.